All right, we're doing inverse derivatives. So a quick reminder of what this means. Okay, I want you to draw or look at a visual. You don't need to draw this picture, but I'm going to show you again what this is. So if you had a graph like this, and this ordered pair was 2, 3, the inverse of that graph would be a graph that looks like that. And then you would have a point on this graph. If these two things are inverses, if that one has a point at 2, 3, what would be on this new graph? 3, 2. If the slope at this point, let's call it 3, what would the slope at that point right there be? It would be 1/3. That is what we're trying to remember. Inverse points have reciprocal slopes. Inverse points have reciprocal slopes. So if you have a point on an inverse graph, the slope is going to be the reciprocal. So remember when we did these things, we got something like this. You would have an original ordered pair. You would have an inverse ordered pair. And they would ask you a question like, find H prime at A. Okay, at some number, H prime at A. If I want to find H prime at A, what does that mean about my inverse ordered pair? What thing do I know? A. I know my X value is A. Let's just, for the sake of argument, say that my Y value is B. What does that tell you about your original ordered pair? What do you know now? It's the opposite of that. It's BA. And in order for me to find H prime at A, you need to know F prime, or whatever the original one's called, at which of those two letters? At B, at this one's X value. You find this answer, and whatever you get, the answer is going to be 1 over F prime at B, or in other words, the reciprocal. This is a tough concept. It's a really weird thing. If this doesn't make sense to you, go back to your notes. I'm spending 3 minutes going over something that took us a couple days to learn. Down below, you've got an example of this. Talk with your neighbors. See how much you can remember without me holding your hand. We look at this problem. Since it says this right here, as soon as I read this, ooh, H and F are inverses. I'm going to set up my paper for success. I'm going to have an original ordered pair. I'm going to have an inverse ordered pair. In the end, what is the ultimate goal here? H prime at 9, the derivative at 9. So that is going to be my inverse. That's what I'm looking for. Okay? If it was the original one, then I wouldn't need to do all this work. That's my inverse, H prime at 9. That's what I'm looking for. All right, cool. That means my inverse function is called H. That means my original function is called F. I know what my X value is. It's 9. If this is 9, then that is 9. Because the A's and the B, or the X's and the Y's would flip. If my Y value is 9 for F, what's my X value going to be? 2, because of this right here. This is my Y. This is my X. So this guy right here is going to be 2. That means this guy right there is going to be 2. Cool. I still haven't done any derivatives yet, so until you do derivatives, you're not doing anything. The original is F. That means I want to find the derivative of the original one at which number? At 2 or 9? 2, because we want to find derivatives at X values. So I'm finding F prime at 2. Well, according to this up here, F prime at 2 is 1/2. If this guy is a half, when I do the derivative of the inverse, what's my answer going to be? 2, the reciprocal of 1/2, which gets me 2. Questions on inverses. That is one that once you get it, it's easy. But you might need to practice once or twice before our exam to make sure you're good at that. Okay, make sure you've gone over those types of problems. Let's go to the next one, inverse trig. Okay, remember there's a lot of inverse trig. We could do arc cosecant and arc secant and everything else. I'm only asking you to remember 2. Okay, so with your neighbor, remind yourself, if I told you f of x was the arc sine of u, find f prime. And let's say g of x was the arc, let's not do arc tangent, let's do inverse tangent of u. Find g prime. Take a second with your neighbor, see if you can remember those two. I am not shocked that this is not one that you're perfect at. Okay? This one is tough. I'm going to remind you of it today, and you should remember it for your test on Wednesday next week. Okay? And then you'll probably forget it again. And in April, when we start reviewing for the AP exam, you're going to remember it again. And that's perfectly fine. This is not one that you're going to have memorized all the time. This is the one, like the night before the test, I'm going to stare at it and see if I can memorize it and then see if you can use it. Okay? That's it. Don't make it tougher than that. Anybody remember arc sine? What's it going to be on top? 1 over square root 1 minus the baby squared times the derivative of the baby. Okay? 1 over the square root of 1 minus the baby squared times the derivative of the baby, where the u is our baby. Let's do arc tangent. Remember, arc tangent and arc sine are very similar. They're not exactly the same. There's a little bit different. The top is the same. There are two things that are changing. What's the biggest thing that's changing? No square root, so it's just 1. And the baby squared, what else changes? It's a plus sign in between instead of minus. Okay? And then it's times u prime. Once you've got those memorized, then it's just a matter of doing it. That's what y is. Y is equal to inverse cosine. So if I find y prime, ooh no, arc cosine, I didn't write that one down up here. What's different about arc cosine and arc sine? It's a negative on top. It's a negative 1 on top. And then on bottom, it's the square root of 1 minus the baby squared times the derivative of the baby. What's the derivative of the baby going to be? Done. Find the derivative of arctangent. So if I'm taking the derivative here, it is 1 over 1 plus, what's going to happen here if I'm taking the square root of x and I'm squaring it? Just x. I'm taking the derivative here. Allie, what's the derivative of square root of x going to give me? Yes, ma'am. 1/2 x to negative 1/2. That is the derivative of arctangent. Could we simplify it? Yep. Do I want to? Nope. So I'll move on. Questions there? Let's go to implicit. Implicit is something we use quite a bit. There's some rules for it a little bit, but at the same time, it's just kind of understanding it. Just some quick reminders of implicit. Okay. First, okay, we use this when y is not by itself. So if y is in your problem, then technically you should in your brain be thinking, oh yeah, that's the implicit stuff. Okay? When we do this, when we do implicit, when you take the derivative of y, what do you have to do when you take the derivative of y? You must add dy over dx. That's what implicit does. Okay, so for example, if I gave you the problem 2y and asked you to take the derivative of it, what is the derivative of 2y going to get you? 2 dy over dx. If you forget, think about what's the derivative of 2x. Well, the derivative of 2x is 2. Oh yeah, but it's y, so I include dy dx. If I asked you to take the derivative of 2y squared, what would the derivative of 2y squared get you? 4y dy over dx. A reminder, you can do these problems a little bit different ways, but if you have two terms, with dy over dx, if you have two terms with dy over dx, don't forget that we can factor it out. Okay? Factoring it out helps us in a lot of cases for these problems. All right, let's do an example here. So it says, write the equation of the normal line to the ellipse x squared minus xy plus y squared is equal to 7 at that point. So down here at the bottom of my paper, I'm writing the equation of a normal line. All right, cool. So I need this. Y minus x minus point slope form. I know what my point is. It's negative 1, 2. So it's x plus 1, y minus 2. All I have left to find is the slope. To find the slope, I'm going to take the derivative of that guy right there. Everybody go with me to this point. Let's take the derivative. All right, you can do it on your own for a second. I'll give you about a 30-second head start. Here we go. We're taking the derivative. If I'm taking the derivative x squared, Lauren, what'd you take the derivative x squared to get? 2x. Then the tricky part here is the derivative of negative xy. Somebody want to take a shot at that one? Negative xy. Angela, what you got for me? So, what rule am I going to need here to take the derivative of negative xy? Product rule, because I got two variables and they're multiplied together. So I've got negative x and I've got y here. Okay, negative x and I've got y. It's in two separate parts here. So if I'm taking the derivative of that, TJ, walk me through that. All right, so you're going to do it the weird way. You could technically do it without the negative. I'm going to do it with the negative, so I'm not making any of you talk. It's me. Negative x, that's my first part. Okay, you could do it the other way. I'm just kidding. I just don't like it. Times the derivative of the second. What's the derivative of y going to get us? dy over dx plus the second. So in this case, my second is going to be y times the derivative of the first. This would be the one place that you might differ from me, but the derivative of the first is negative 1. Somehow, you need that second part to have a negative in it. Whether you do what TJ said and factor the negative out and put it in parentheses and distribute it at the end, that's fine. I'm going to do it that way. Then I'm taking the derivative of y squared. The derivative of y squared is 2y. dy over dx. And then I'm going to make that all equal to 7. Yeah, 0, because the derivative of 7 is 0. Good. I just remind you, because I always screw that up, so I like to tell you the same. There's my answer. Everybody go with that? If we're finding this derivative at a point, I would suggest to you to just plug in negative 1 and 2 at this point. I'm going to show you to get dy dx by itself, just that way we can see a variety of problems here. Okay, so I'm going to get dy dx by itself. So to do that, I'm going to move anything that doesn't have dy dx over. So this 2x needs to move over, and this negative y needs to move over. So I'm going to get stuck with this problem. Negative x dy over dx plus 2y dy over dx is equal to, on the other side, I'm getting negative 2x and then plus y. Moved all the dy dx's on one side, moved everything else to the other. At this point, I want to get dy dx by itself. So what can I do with these two things to get dy dx by themselves? I can't combine them together. I'm going to factor out what they share, and they both have a dy dx in them. So if I factor out a dy dx, then I'm left with this, negative x plus 2y. Then I'm going to get dy dx by itself, so that means I'm going to divide by negative x plus 2y. So dy dx equals that thing. Find the slope that goes in for that normal line there. Talk with your neighbor, find the slope that goes in for that normal line. I plug in negative 1, 2. I take this point, I plug it in. When you plug it into that right there, what do you end up with? You get 4/5. Somebody back me up on that? You get 4/5. If that was 4/5, what number am I plugging in for slope if I'm writing the equation of the tangent line? Negative 5 over 4, because what does normal line mean? Opposite reciprocal. It means the perpendicular slope. So it is negative 5/4 right there. Questions on equations of a normal line? Let's do the last one here. We're doing related rates. I had to kind of pull this in, so I already filled in the blanks. Remember some rules for related rates. First thing we do is we label everything. We identify the problem. We make sure we label rates as the derivative of something over time and consider their signs. Remember, if something's getting bigger, it's going to have a positive sign. If something's getting smaller, then it's going to have a negative sign. Determine if something never changes. Remember that ladder leaning up against the wall, sliding down. The ladder's never going to change signs, so it doesn't have a rate. So it's going to be a constant. Then you got to find some sort of equation that relates all those variables together. We plug in the constants, we take the derivative with respect to time, and then you plug in your actual answers to get that all squared away. With your neighbor, read through that question and do some labeling and see what you can get. See if you can think of what equation you need to set that up. So we've got a balloon. It's spherical. Oh, that is not spherical. Oh, that is so bad. I apologize to everyone that had to see that. All right, now we got a balloon. It's spherical. That is a perfect balloon. I will not take any of your slander. Jordan, what's something you labeled on this thing? dr over dt, so the change in radius over time. What do you say that was? Disagree with that. We're looking at what rate is the radius increasing. So that's what we're looking for. dr over dt is our goal here. We're trying to figure out the change in radius over time. So that's what I'm looking for. This 3 pi up here, what can we label that 3 pi to be? That's a change in volume, and that's a little bit weird to see, but it's the air that's coming into the balloon. The thing that would help me there with anything else is the units. Because it's feet cubed per minute, that's kind of telling me, oh yeah, that's a volume type setup. That is the change in volume over time, 3 pi. Is it going to be a positive 3 pi or negative 3 pi? Positive, because air is going into the balloon. We got one other thing here. The radius is 3 feet, and that's definitely positive because it's a radius. Cool. There's my 3 things. They didn't tell me anything else. I need an equation. What equation is going to relate the volume of that balloon and the radius? Volume. I would strongly hope that they gave us the equation here. This would be the one that they'd be like, if they wanted to be super jerks, they would need you to memorize it. I don't have it memorized. I could not tell you that 4/3 pi r cubed off the top of my head. So if you got to that, you would take the L. But I would expect that they would. Okay, so let's say I gave you that equation, 4/3 pi r cubed. Is anything constant here? Is there anything that's not going to change? Because if it wasn't going to change, I would plug it in now before I took the derivative. But everything is changing, so we're going to take the derivative at this point. The derivative of volume is dv over dt. Which one do I need here? Do I need product rule or chain rule to take that derivative? Neither. There's neither. There's not 2 variables. There's not parentheses. It's just regular power rule. We're going to multiply by that 3. So it's 4 pi r squared. Don't forget 4 pi r squared. I just took the derivative of r with respect to t. So it's dr dt over there. I'm going to plug in what I know. dv dt is 3 pi. R squared, my radius, is going to be 3. And then dr dt, I'm getting that by itself. 3 pi equals 36 pi dr dt. Divide by 36 pi. Divide by 36 pi. The change in radius over time is equal to 1/12 feet per inch, or feet per minute, sorry. Feet per inch, feet per minute. It doesn't ask for units, so I'm not going to be too worried about it.